Yeah, so today we will be discussing, Droop characteristics in synchronous machines. So do you have any idea about that? So there are certain frequencies at which some machines operate, and when they are in parallel or such that, let's say for infinite bus, there are many alternators connected. Okay, they will be supplying many loads that may be variable or constant for a particular amount of time. So, at what particular frequency they should operate, you know, that makes it very critical for operation of power systems. So, what we will do today, we will take couple of questions, and with the questions, we will try to, you know, see what happens when frequency changes and all. So, I hope my screen. is- Okay, so I hope now it is visible. So I will be taking a couple of questions. With questions, we will clarify our idea about loop characteristics, basically. Okay. So we have a generator that supplies a load. Okay. We have a load. Okay. And now we are connecting another load in parallel. Okay. But generator has a no load frequency of 61 hertz, and its slope is 1 megawatt per hertz. Okay. So at to supply 1 megawatt of power, its frequency will drop from 61 to how much? If let's say the alternator is running at no load, now you are adding a load of 1 megawatt to this particular generator having such characteristics. So what will be the frequency of the generator?
60 hertz.
60 hertz, exactly. So that's what the characteristics is. It does imply, right? So now I am giving some numbers. Okay. Load one, let's say it is taking 1 megawatt at certain power factor will be there, right? So zero point 0.8 power factor lagging, I am saying. Load 2, I am implying it zero point 0.8 megawatt at 0.707 power factors lagging. Okay. We are connecting two loads to this generator. Okay. Now we need to find out the frequency of the alternator or operating frequency of the system, basically at what frequency this system should work so that it this generator can cater to the demand of both the loads. Okay, so we will move ahead with certain expressions. Okay, now frequency of the system, we can write it as frequency at no load minus power that much is required divided by slope. Okay, does this make sense? I hope it is a pretty simple expression. Okay, just from here that you told that after adding 1 megawatt of power, the frequency of the generator will be 60 hertz. Simply, I am writing it in terms of expressions. Is there any problem with this particular equation?
No, sir, clear.
Clear. Okay, great. So I'm moving ahead. So I want to know when. load 1 was only connected, what will be the frequency of the system will become, and after that, when both of the loads will be connected, what will be the frequency of the system. Okay, so no load frequency is 61 minus power demand is 1000 kilowatt or 1 megawatt. So 1 megawatt divided by slope is 1 megawatt per hertz. So after load 1 only connected, it will become 60 hertz. Now, after both load 1 and 2 connected, frequency of the system will be 61 minus total power is 1 megawatt and zero point 0.8 megawatt. So 1.8 megawatt divided by 1 megawatt per hertz. So it will become 59.2 hertz. So as you keep on increasing the load, your droop in frequency you can observe. So the characteristics is something like this. This is the power, this is frequency. Okay, so this is known as the droop characteristics. Okay, I hope it is fine till now. Now I want to operate the system frequency at 60 hertz. What corrective action should I take? I want system frequency after both loads are connected to be 60 hertz. You could do anyone, you are free to do anything. What action you would take? So you can, what you can do here, like uh, from 61 to 59.2, so total of 1.8 hertz droop we are observing. We want the droop of only 1 hertz, right? Such that the system frequency will be 60 hertz. So if droop is equal to only 1 hertz, then our no load frequency should be increased by zero point 0.8 hertz. So earlier it was 61, now it should be 61.8 hertz, such that after connecting both the loads, it should operate, the system should operate at 60 hertz. Okay, does that make sense? Okay, any doubt, any final doubt in this particular problem?
Sir,
Yeah,
we connect first load, then frequency is 59.2, and we connect both the load, then 61.8.
no,
Uh,
no. See, when I connected first load, then the frequency of the system dropped to 60 hertz, right? From 61 to 60 here. After I connected both the loads, then it drops to 59.2 hertz. But I want to operate it at 60 hertz. So what should I do? I should increase the system or generator frequency by zero point 0.8 hertz, right?
yes, sir.
Yeah. So that's what it does. Okay. Any final doubt in this? So there are some gate problems which we will deal in last of the session. Two questions which was asked on the parallel operation of alternators and group characteristics, which we will discuss in the last. So let me take one uh, qualitative problem. Okay. So now we are having two generators. Okay. supplying a load. Okay, so generator 1 is operating at no load frequency of 61.5 hertz, and its slope is 1 megawatt per hertz. Similarly, generator 2 has no load frequency of 61 hertz, and its slope is again 1 megawatt per hertz. Now, the total power these two generators are supplying, okay, is equal to 2.5 megawatt at zero point 0.8 power factor lagging. Now, the question in front of us is at what frequency the system should operate, okay, and what should be the ratios of power and what should be the contribution from each of the generators to the load, okay. So at what system frequency they should operate, okay, another is how much power is supplied by each generator. Okay, so I want to have your ideas how to move ahead on this particular problem. You got the question? Any doubt in question?
Okay.
I'm sorry, your voice is breaking. Could you please repeat? What did you want to say?
No doubt, sir.
Okay. Great. So, any suggestion you want to make here how to move ahead with this kind of question? Okay, and they are very much relevant. That such questions could be asked either from power system or synchronous machine. Okay, so basically, first what we should do, 2.5 megawatt would be supplied from generator 1 and generator 2. Okay, that's for sure. Now, the expression of power is what? Means I am asking what is the expression of power. So it will be slope, right? Megawatt per hertz into hertz, right? So first thing is slope of this first generator into no load frequency minus at what common frequency the system will operate. Okay. Similarly, for second generator, the slope of the second generator into its no load frequency minus the system frequency at which the system will operate. I can equate it to 2.5 megawatt. Is there any doubt in this step? Yeah, yeah. So the power supplied by the generator, each generator will be in terms of it should be in terms of what, right? So if you combine this expression, it is nothing but megawatt. Its unit is megawatt per hertz, and its unit is hertz, right? So both will be multiplied, and it will give you the operating power at which this particular alternator will operate. Okay. So how much power is supplied from the generator one? will be given from the first expression, this expression, okay, and how much power will be supplied from the second alternator, that will be given from the second component of this expression. And this power is dependent of what is the no load frequency of the machine, okay, what is the slope of the machine, what is the droop characteristics of the machine. So these two things defines how much power will be supplied from each of the alternators.
Got it, sir. Thank you, sir.
Yeah, great. So now I can equate it further. So the slope of first alternator is actually both alternators are 1 megawatt per hertz. So I can write 1 megawatt per hertz into no load frequency of the first alternator is 61.5, and we want to find out the system frequency, okay, plus slope of the second alternator is again 1 megawatt per hertz, and its no load frequency is 61 minus frequency of the system. We want to find out the frequency of the system, and it is equal to 2.5 megawatt. 2.5 is equal to 61.5 minus F system plus 61 minus F system. Okay, so can you solve it now? 122.5 minus 2. So I guess 60 hertz you will get.
60 Hz.
60 hertz, yes. So this is the operating frequency at the system will operate. Now can we find out how much the power has been supplied from the alternator 1 and alternator 2? I want to find out the P1 and P2. Can we find it out?
1.5 megawatt P1.
Sorry, repeat please.
P1 1.5 megawatt.
P1 is 1.5 megawatt, okay.
P2 1 megawatt.
P2 1 megawatt. Great. So how did you calculate? You just put the value of system frequency in this particular expression and this particular expression, right?
Yes, sir.
Yeah, great. Thanks a lot. So this is the way, and if you add, so you can see that both will lead to 2.5 megawatt. So the system which had higher no load frequency, okay, and whose droop characteristic actually droop characteristics of both the alternators were same, but those who had the higher no load frequency ended up providing higher power. That you can conclude here, right? So P1 had the no load frequency of 61.5. So mm, to maintaining the common frequency of the system, okay, so droop in the higher no load frequency machine is higher than the lower no load frequency machine. That's why P1 is able to contribute more in the system. So basically, if you want to operate, if you want to supply higher power, you just need to increase the no load frequency of the machine if your droop characteristics are same. Otherwise, you can improve the droop characteristics as well. That is another way, right? So I hope it is this part is clear to you. Now, in this particular problem, if an additional 1 megawatt, part B of this particular problem, I want answer from you. If additional 1 megawatt load is attached, what will be the new system frequency and the power delivered from G1 and G2? I want answer from you guys. Okay. So are you able to solve? I guess it is pretty easy problem, right? Is anyone at?
Frequency
Yeah, go ahead, guys.
59.5.
59.5, sir. Frequency.
50,
59.5.
59.5. Yeah, that's correct. And what is the power supplied from the generator 1 and generator 2?
Generator 1, 2 megawatt.
Uh,
P1, P1,
P1 is how much?
2 megawatt. 2
2 megawatt.
megawatt.
Exactly. And P2 is 1.5
Eight-
megawatt.
Yes, sir. Yes, sir.
Yeah, great. So I hope you got the idea of such kind of problems. Okay, you just practice based on this and you will be fine. Okay. So moving on with the next problem. Okay. So I hope you are able to see the problem.
Visible,
Yeah.
sir.
Yeah. So a 480 volt, 250 kVA, zero point 0.8 power factor lagging, two pole, three phase, 60 hertz synchronous generators. So this is the generator one characteristics. Let me highlight it. No load speed of 3650 RPM and full load speed of 3570 RPM. It is operating in a parallel with another alternator with its characteristics like this. Okay, this is different four pole 60 hertz synchronous generator, and its no load speed is 1800 RPM and full load speed is 1780 RPM. The load that is being supplied by these two generators is of 300 kilowatt and zero point 0.8 power factor lagging. Okay, so now first question I want to ask is how much a speed loops of the generator 1 and generator 2 will be. So a speed loop, I mean, let me define it for you. A speed loop is nothing but no load speed. minus full load speed divided by full load speed into 100%. Okay, so this is the speed loop expression.
Generated one 2.19 percentage.
Generate
2.19.
generator one 2.19 percentage. Okay, so the no load speed you can easily calculate, or it is given, right? 3650. But yeah,
Generated to 1.123 percentage.
to 1.12 you are saying?
Yes, sir. 1.123 percentage.
Yeah, yeah, that's correct. So both these values are correct. So could you please let us know how did you solve it?
Sir.
Yeah, yeah.
Hello.
Go ahead,
See.
please. Huh.
So no load speed minus full load speed divided by full load speed into 100, sir, by using this
Ye-
formula, sir.
Yeah, yeah. So full load speed, no load speed is given directly in the problem, right?
Yes, sir.
So, and full load speed is also given in the problem, right?
Yes,
So
sir.
both were pretty apparent. So there are no doubt about it. Okay. And you just plug in these expressions to get the result. That's all, right?
Yes, sir.
Yeah, great. So that was pretty easy part. So now the thing which we have been learning. So we have to now find out the operating frequency of this system. So how will you find the operating frequency of the system?
Based on NS equal to 125p.
Huh. So see, to find out the operating frequency of the system, we must be aware about the power saving by each generators, right? So, and to know the power saving by each generators, we must be aware about the droop characteristics of the or the slope of the machines, right? So, uh, first thing first, okay, uh, how much is the power output or maximum power supplied by each generators that we will see. So, uh, let me write it here. The maximum power or the power can be supplied from the generator 1 at full load will be how much?
200, 200, 200
200, 200 kilowatt. How he is saying 200 kilowatt? Because we have 250 kVA in 2.8 of power factor, right? So it will lead to 200 kilowatt. Now, the power can be supplied from the second alternator is,
to 212.5 kilowatt.
yes, 212.5 kilowatt. Okay. And now this power can be written as, you know, slope into no load speed minus full load speed. Okay. So we want the slope of both the machines. So I want to find the slope of first machine, which is 200 kilowatt divided by no load frequency is corresponding to this speed 3650. How much will be the no load frequency? And corresponding to this full load speed 3570, how much will be the frequency?
Generator 1 no load frequency 60.833 Hz.
Yes. And its full load frequency is
Can you show it problem? Can you show the problem? Given that.
okay. Yeah. Corresponding 3570 RPM, and this pole is to
59.5 Hz.
59.5. Okay. So it will lead to something 1.3,
150, 150.037.
150 150 kilowatt per hertz, right?
Yes, sir.
Because this is kilowatt. So see, the thing is why you might have the question why we are calculating the droop characteristics even though we have got the full load power, right? So do you have the answer for this? Even though we have already calculated the power, okay, supplied by the both the alternators at full load, but still we are interested in finding the droop characteristics. Why are we doing that? So in the meanwhile, who are not able to think, you find the slope of second alternator. Okay. So see, both the alternators combined can produce the power of 200 plus 212.5, that is 412.5 kilowatt. Okay. But the load requirement is 300 kilowatt only. Okay. From the question, if you see, the load requirement is 300 kilowatt only. So now there will be some ratio in which both the alternators must be supplying power. Okay. And that will be determined from the droop characteristics. That's why we are interested in calculating droop characteristics. I hope you get it, right? Okay,
Generator 2
so
no load frequency 30 Hz.
okay, so what could you please repeat? What are the no load and full load frequencies?
Generator 2 no load frequency 30 Hz.
No, it should not be 30, it should be 60 because here pole numbers has been changed.
Oh,
Did you consider four pole?
okay.
Okay.
Okay, sir.
Yeah. So 60 minus, just divide that full load by 2. So you will get
50,
that
59, 59.32.
59.32. Yeah. So how much it will produce?
312.5.
Okay. So 318.5 kilowatt per hour. Okay. So we have got
Sir,
the
312, sir. 312.
312. Okay. 312.5 kilowatt per hertz we have achieved. Now
Yes, sir.
we wanted the system frequency, right? So system frequency, I would like to just plug in those values. Okay. Just like we did in the previous question. So total power is 300 kilowatt. That is load power is required. Okay. And slope one is 150 kilowatt per hertz. And its no load frequency is 60.833 minus system frequency. So that we are interested in, right? The other component will be 212.5 kilowatt, sorry, 312.5 kilowatt per hertz into its no load frequency is 60 minus system frequency. Okay, so now I think you will be able to find out the system frequency, and that will be the frequency at which this entire power system will work.
Fif- 59.62 Hz.
58.2 you are saying?
No, no, sir. 59, sir. 59.62.
59.62. Okay, so I hope everyone is getting the same answer. Anyone else has calculated it? Okay, if you haven't calculated, calculate it after the session. Okay. So yeah, so now is the time to solve a gate problem, couple of gate problems which I have taken. Okay, so did it go? Yeah, so here it is. Yeah, this was the problem which was asked in gate exam. So you can see power system has. I think you are able to see the gate problem, right?
Sir, visible, sir.
Yeah, yeah. Thanks. So a power system has two synchronous generators. Characteristics are given in terms of here that P1 and P2, where F denotes the frequency in hertz and all. The power outputs of turbine 1 and 2 are in megawatt. Okay. Now we are interested in load. So total load is 400 megawatt. We can equate it to P1 and P2. Okay. So I can write 50 into 50 minus F plus 100 into 51 minus F. Okay, so I hope you are able to identify, even though it is not mentioned, that this 50 and this 100 are slope, and these 50 and 51 are the, what are they? These 50 and 51 are the
No load frequency.
no load frequencies of separate alternators. Yeah. So we want that at 400 megawatt, what will be the frequency of the system? Okay, so I hope it is pretty easy since we have solved a couple of questions earlier. So it will lead to 400 megawatt into uh, 50. I will take common.
48 sir.
How much you are getting?
48 sir. 40.
40. So frequency will be 48 hertz. The system frequency will be. Okay, everyone is getting 48, I guess. Okay, so I hope it is fine. Another problem that should be a bit good. Yeah. So this problem, I think it will use some of our brains. So yeah, I hope you are able to see the problem. So a single 50 hertz synchronous generator on Droop control was delivering 100 megawatt power to a system. Single generator initially, they were delivering that was delivering 100 megawatt power. Now, uh, due to increase in load, generator power had to be increased by 10 megawatt, as a result of which system frequency dropped to 49.75 hertz. Okay. A further increase in load in the system resulted in the frequency of 49.25 hertz. At this condition, how much power will be supplied by the generator? Okay, so there are two, three conditions. We should move step by step. So at 50 hertz, 100 megawatt power was being delivered. So let me write 100 megawatt is equal to, you know, uh, certain characteristics will be there. So if no load minus that frequency into slope. Okay, so now if 10 megawatt is increased, now it will have if no load minus this frequency is 49.75 into slope, right? So now we have two unknowns, two equations. Here we will find out no load frequency and the slope of the generator. Okay, so there is this way we can solve by solving two equations. Another way is to finding the slope directly is, by increasing 10 megawatt, the droop which we can observe directly from the question is from 50 to 49.75. So 0.25. Okay. So can we say that the slope is 40 megawatt per hertz? Can we say this?
40 megawatt.
Yeah. So if we can say that 40 megawatt per hertz, and in the question it is being asked that a further increase in load resulted in 49.2 hertz, 49.25 hertz. So from 50 to 49.25, so it is how much? 0.75 hertz. So 0.75 hertz from the initial condition, I am counting it from 50 to 49.25, and initial power was 100. Okay, so let me find out the power at this droop. So by the droop of 0.75, can I say that 40 megawatt per hertz is the droop characteristics, and the droop in the frequency is 0.75. So This
30, 30.
30, 30 megawatt. So this much power will be, is this the answer of this problem? At this condition, the power in megawatt supplied by the generator. Read the question very carefully. That's where you might get trapped in the exam. So will the answer be 30 megawatt or not?
Answer 130 megawatts, sir.
Answer is 130 megawatt, exactly. So answer is 130 megawatt. Why 130 megawatt? Why not 30?
Already we have 100 megawatts, sir.
Yes, at 50 hertz already the initial condition is 100 megawatt of power. From that condition, we are observing this much of drop. Okay. So we have to consider that initial value of 100 megawatt first. And then we need to add in the system, right? So that's why it will be 130 megawatt.
Sir,
Yeah.
so why we have not taken 40 megawatts per head, sir?
Why we haven't taken 40 megawatt per hertz?
Yes, sir.
Yeah, that is being taken, no? So see, 40 megawatt per hertz is the slope of the this alternator, right? And the droop we are observing from 50 to 49.25, this values from 50 to 49.25. Okay, that droop we are multiplying into that this 40 megawatt per hertz into that difference of the frequency from 50 to 49.25, the difference is 0.75. So that difference we are multiplying it here to get how much by reducing that much of frequency. Okay, how much is the power we are we are basically providing to the load, to that increased load. So how much the load will be increased?
Yes, sir.
Yeah. So
Sir,
that
and what
yeah.
is a speed group characters means what it will express, sir?
Okay. So it a speed and frequency loop both are the same. Both characteristics are the same. So it signifies that as you are increasing the power, the load, okay, as you are loading the machine, your frequency and the speed of the machine is gonna be reduced proportionally or whatever the characteristics of the machine is. So that characteristics we justify in terms of megawatt per hertz or watt per hertz. So power by frequency. So this droop or this slope is determines that how much power you are increasing and how much drop in the speed and frequency of the machine will be.
Okay, sir. Thank you, sir.
Yeah. So I hope now you will be able to solve any problem based on these droop characteristics. Just practice a couple of more problems on your own, on a regular interval, and you will be good. Okay, so that's all from my side on this particular topic. Okay, so in next session, what do you guys want to have? Do you have any preferences, or just I am going fine? You can let me know.
Sir, you can say latest problems which are in missions and we can explain them, sir.
Latest problems on machines.
It means last year paper, what are the type of questions they are asking, and you can
Okay,
just go through.
see, that particular thing is already done on the NPTEL portal. Okay, so on NPTEL Gate portal you visit, you will find almost all the solutions of the problem, past year, even recent year problems also. Okay, so that is being handled by different kind of teams. Okay, but anyway, if I get time, I will take those explicitly if you want. But that is already being done, so it will be, you will be attending sessions, so you are not gaining anything extra. So,
Sir, fault analysis, sir, from
a
process.
fault analysis, okay, fault analysis, that is the part of power system. system. I was asking specifically related to synchronous machine as of now. In this particular
Sir,
synchronous
related
machine,
to
yeah,
sir,
guys,
related to V inverted vehicle, sir.
related to V and inverted vehicle. Okay, that is a very good topic. So V and yeah,
Problems on voltage regulation.
problem on voltage regulation of synchronous machine, right?
Yes, sir, synchronous.
Voltage regulation. Okay.
And
Okay.
the,
So
and the
yeah,
EMF equation of synchronous machine, sir.
EMF equations
How to calculate KD,
for
distribution factor, pitch
distribution
factor.
factor and pitch factor. Okay. Okay. So okay. So I will keep these three topics in focus. Okay. Okay. Anything else? So initially we will go ahead with EMF equations, okay, and then voltage regulation and 2V and inverted V curves. So in next lecture, I think we will mostly be focused on EMF equations. Okay, will that be fine for everyone?
Okay, sir.
Yes, sir.
Okay,
Sir,
great, great, great. So
sir,
yeah,
we want this PDF, sir, to get this
okay, okay. PDF. Okay, yeah. So that's a bit tricky part, but anyway, are you getting lectures on YouTube?
Yes, sir, yes, sir.
Okay, so I will attach PDF also. Okay. I I I will try to attach the PDF in the description box. I will attach.
Oh,
Okay. Okay. Thank you very much, guys. See you on the next Friday.
thank you,
Bye
sir.
bye. Yeah. Bye.
Thank you, sir.
Thank you very much. Bye.